So for the motor joint system, you can see that that's a typical circuitry we use for the motor joint. So in the front end here, we have the square wave applied to the motor. So last week we mentioned about the DC voltage will be pure DC. Now, of course, in this case, we cannot use a DC to control the motor. And the input side, we usually use a square wave to do that. That will be conducted by power electronics. We use power electronics to produce a square wave on the input side. So probably input can be any DC voltage here, DC voltage, but in here we're going to have a square wave. So we are using this kind of square wave. That means we can regulate the duty ratio here. The duty ratio here, we can control the average voltage produced to the DC motor. So that's to say that would be more electronic control because we cannot use a pure DC source to do that. We won't use a power supply to adjust the voltage. We won't do that. But at least here we can use some electronic control to control the duty ratio, apply the voltage to the motor. And then of course for the field, that's a field circuit side, right? The field circuit actually will produce a variable voltage by using chopping method. We can change the voltage here, apply to the field winding. Most of the case, we tend to use a constant field current to do that. But in some case, for instance, when we want to adjust the speed further, we can use the field to do that. For instance, like the field weakening mode, we can able to adjust the field further. So that's a basic configuration. We can see that for DC motor control. But having said that, we're now including the LA component. The inductance component is always there, but before we did not mention it because if we have pure DC operation, the LA will be just more or less disappear because under this condition, the inductance will, in this case, we call it the impedance, will just become zero because omega L. You can see that the impedance for inductor equal to omega L. So if under pure DC condition, then of course the omega U is zero, then the inductance doesn't sound any useful item in the circuitry. But however, now then if we're using this kind of square wave, then we see that inductance when you apply to the inductive component for the DC motor, there will be some reaction. So that's the thing we need to understand further about the motor operation. So that's a typical circuitry. So most of DC motor, we tend to use this so-called separately excited. Although last week we learned motor can be series connection or maybe shunt connection or series parallel, but these series connection are most popular. Then we can able to use DC voltage apply to the armature to adjust the armature voltage and current. And then we can use separate field circuitry to adjust the magnetic field to the motor. So they're commonly being used. So that is straightforward. So the voltage applied to all the DC motor now becomes square wave. So like in here, this simple diagram to show you what kind of voltage applied to square wave, which will be a so-called pulse width modulated waveform. PWM, of course, everybody know, we modulate the voltage, more the pulse width, so that we can adjust the voltage. So the average voltage must proportional to the duty ratio. So for instance, if we got T on time, and the total period is like that, then the duty ratio will be this equal to this one. So this ratio will be obvious from D from 0 to 1, right? So that's similar to all the other converter. So then the average voltage just linear proportional to the DC input voltage. So if the V on is the amplitude, the peak voltage for the square wave, so maximum voltage, if we turn on all the time, become V on, but if we do not turn on, becomes 0. So the average voltage applied to them proportional to D, the duty ratio. So that's a typical agree with all the power electronic conversion system. So the duty ratio can be anything. For instance, in here, it can be a really small pulse or large pulse, depending on your voltage control. Usually for DC motor, we don't use really small pulse because it's not very effective, not good efficiency. So usually the pulse will be say 0.3 to 0.7 will be quite common. Anything less than 0.1, the motor doesn't have good performance anyway, because the ripple will be large and also the efficiency getting lower because we tend to only energize the motor for small little duration and then let the motor continue to release the energy. So the performance may not be too good. But anyway, we can use this duty ratio method to control the voltage. So this simple pulse show you some possibility how we control the DC motor. Like in here, for instance, we got T1 equal to 0.2, T2 0.8, then the period here will be summation. So the period, like the switching period will equal this one, then the duty ratio off is equal to 0.2. And then the frequency will be equal to 1 over the period equal to 1 kilohertz. And the average voltage, again, we use duty ratio multiplied by peak voltage equal to 2 volt. So for motor operation, the frequency are quite a big variation. Anybody can tell me what's the common frequency we apply to the DC motor? Servo, do you have any suggestion? What kind of voltage, switching frequency voltage we apply to a DC motor? What's the common frequency we use? Okay. Manvia, do you have any recommendation?
80 kilowatts.
80 kilohertz? Yeah. And the frequency we use usually can be from, say, 1 kilohertz for a large motor. Then you can go up to really large, can be, say, something like 100 kilohertz also become possible. Yeah. But obviously in the industrial joint, for something like 50 kilowatt motor, I mean, also something like 20 kilohertz will be also quite common. Someone will say, why don't we use higher than 20 kilohertz all the time? Because the human being cannot hear more than 20 kilohertz. But that may not be the case. Because sometimes for a large power motor, 20 kilohertz will be quite difficult for the large motor. Because the large motor, we cannot use too high frequencies because current voltage, heavy weight will be large. Then the too high frequency, the motor may not able to respond properly. So that means even though you can see that for instance, like the train application, cross-country train, railway system, the frequency is not really high. It's 10 kilohertz, maybe something even lower. Because for instance, they're using GTO. I'm not quite sure you know about high power switching device called the GTO, gate turn off thyristor, or thyristor. Have you learned about thyristor? Thyristor, have you learned thyristor before? Servo, have you learned power device, thyristor? Yeah. Yeah, thyristor is this, okay, yeah. That's the same symbol, thyristor. Then this kind of device usually for powertrain. Then the power can be megawatt power. They can switch. Then of course they cannot switch megawatt at 100 kilohertz. Usually just 5K, 10K as a really, really maximum. 2K quite common. So that means the frequency all depend on the motor we tend to use. So that means the range can be from 1K to 100K hertz. For robotic control, it can go up to 100K hertz because we need really high speed control. Even old days, some motor can be less than 1 kilohertz. Anyway, so that's a really typical circuitry. We call it simple chopper. Chopper means we chopping the waveform on and off to provide the power. So when we turn on the switch, when this switch is being turned on, then you turn on, then this voltage will deliver the current directly to the motor in such a way, right? Then that means the motor voltage, when switch is on, will therefore equal to input DC voltage, VM voltage. Obviously, that will be the case. And then, as I say, we try to use the switch to adjust the voltage delivered to the motor. So after a certain duty ratio, we turn it off. So when we turn off, then this once it turn off, then the current, let me see if it changes. We'll try to change the color, but it's not such. So, but when we turn off, then of course this current, when off state, this current cannot flow here, right? So, and then what happened? Anybody can tell me what happened if we turn off the S? No current can be delivered from the source, DC source, to the motor. Then would there be any motor current?
There will be still current.
Still motor current, right? Servo, do you think there's still current in the motor?
There will be some.
If we turn off the S.
Because of the inductor.
Yeah, that's still okay. Yeah, because inside the motor there's a LM, the inductor LA, right? The inductor will continue to flow, keep the current to flow. the motor cannot stop instantly. Yeah. So that means that's all the characteristic for all the inductive component, including motor and transformer. So that is to say, the current still continue to flow, but it cannot flow through the S. So the only way you can flow through will be flow through the diode. That is the function for the diode, to make sure the current can continue to flow. Without the diode, the current cannot go anywhere. That can be disaster. That will create a high spark, high voltage, will damage the motor. So this diode must be there for a freewheeling diode. I think in terminology, we call it freewheeling. Freewheeling diode to do the job. So that's why when I turn off, the motor voltage becomes 0, because when the diode turn on, the diode is on, right? Diode on, then the voltage across the diode are assumed to be 0, because voltage across it usually just 1 volt, maybe 1 to 2 volt. Then compared to a DC voltage, which supposedly they are look like 0 volt anyway. So that means the current will become like this. The diode current here will therefore equal to armature current. Okay. IDC input here will therefore equal to 0, like that. That was quite simple and straightforward. Obviously, we can get the average voltage to the motor will become D multiplied by VDC, average voltage, the same concept of average voltage. So this is really simple chopper applied to a motor, but most of motor system, DC motor system, depend on this simple circuitry. Of course, there will be more complicated circuitry. We use 2 transistors or 4 transistors to do the job. But in the introduction to DC motor, we first show you using single transistor to do the switching. Any question up to this point? I think you learned them in the past, right? Have you learned them? 10 years ago.
Lecture you went through.
Okay.
Before not.
So another thing we look into with the power level and the current level. So one thing can see that if we still assume the current of the motor still continue to flow of it is, then that's the current for the armature current. So this armature current, if you conduct through here, then these two are equal. But if you conduct through here, these two will be equal. So that means armature current IA will sometimes flow through the IDC DC source or sometimes flow through the diode. So in here, you can see that the IDC, the input side, input source current will behave as a square wave. The square wave will be in the duration proportional to the duty ratio. So that means DC source power will be equal to DC source power. Then we, of course, DC voltage. DC voltage, this DC constant, unchanged, multiplied by the current will be IA multiplied by duty ratio D. As simple as this, right? Any question? Power must be equal to voltage times current, right? But having said that, that one issue will be, if you make a current sensor here to measure the current, and then if I ask you to use a meter, current meter to measure this current, then you have usually the meter, you have RMS meter, you have average meter. Which one you shall use to measure this input current in order to get the power? Do you get my question, right? Measure the power, of course, voltage multiplied by current. Then you put the meter in here to measure the current. Then you can check your meter there. Then usually the meter, they will say true RMS. Have you seen this word? True RMS. In most of the meter, 90% of the meter, they say true RMS. They say they will give you the true exactly RMS current for you. What do you think? Can we measure the motor power using true RMS meter in this scenario? Why is that? Yeah.
After there is current generating.
The thing is, this is average current. That's not RMS current. So that means when you measure DC current in that scenario, don't use true RMS. It's incorrect. It's wrong. That is average current. You need to get another meter for measuring average current. Okay. So that's really critical. The thing is when many students, everybody, even engineer, senior engineer, professor, when they're trying to measure the current, they think, oh, I'm just using RMS meter, measure the current and multiply voltage, then they get the power. That's wrong. Yeah, because in this scenario, if a DC condition under that case, we need to use average. So if one is the DC fixed value, then the other is a non-fixed value, then usually power level will use the average. But if both of them are AC, probably we may need to use RMS. So that is something we need to be careful. So case by case, not all the cases are using RMS. Sometimes RMS, sometimes we use average. Anyway.
Professor.
Yeah.
I have a question.
Yeah.
Only see the source.
Say again.
So, decide whether we only see the source is AC or DC. DC use average and AC use RMS to measure the power.
All the case by case. In this particular case, because input is DC,
yeah,
it happened to be we use average. Happen to be, but sometimes we need to be very careful. You can do it by first principle to work out when it become AC condition, then we have to use RMS, or maybe we need to use the average. All different cases. You can't just say, oh, AC we use RMS or DC we use average. No, that's not that. You need to check the basic formula. Later I got another example to show you what it is. I found that this is although a very simple concept, but people never care. They said randomly to use any one meter to measure. That's not true. I will next few page, I will show you how we get to that. So now then we can see that for operation, then we use this simple chopper to chop the voltage, and then we can develop the waveform as shown here. In here, we're still assuming the armature current still equal to a fixed linear DC current flowing continuously through the motor, even though we use high frequency switching. And then again, we have the current here, DC current will be equal to this square wave, right? As we've done that. And then, so this current will sometimes flow into here, sometimes flow through here. So that's why the transistor voltage, because this is turned on, when the transistor being turned on, of course, there's no voltage across the transistor. When the transistor being turned off, because there's all the resistance in here, you therefore send for all the voltage. So that's why this voltage will become a square wave as such for the transistor voltage. And then for the armature input voltage, then we turn on, of course, that's voltage applied to from the DC source to the motor. And then so the transistor being turned on or so that means Q is on. And then here will be dial is on. So because dial is on, then we have zero voltage. So that's how we see the waveform look like. So key thing is you can see that armature voltage will therefore appear as a square wave. So that means the average voltage, we can using simple averaging, this multiply duty ratio, we can therefore get the voltage across the motor. So, and then now we can see that voltage across the motor becomes square wave. How will that affect the motor equation? Before we just assume a pure DC, but now becomes square wave, we need to double check how the motor equation will look like. So the average voltage in the motor, so that's that's a motor voltage equal to this one. So that's an average voltage applied to the motor. But we haven't touched the current yet. We haven't touched the power level or other item yet. So the voltage appear on the transistor is still a square wave. And so this is the transistor voltage that is still a square wave, as I mentioned before. And the statement here is important, right? The current I always is a DC. Always DC, because as I mentioned, this inductive component, current of motor cannot disappear instantly, even with turn on the input. We're talking about the time domain here. It's not a few minutes. It's a few milliseconds, right? Maybe 1 millisecond or less than 1 millisecond. So even the turn of the power source, of course, after 1 minute or after 15 seconds, you decrease to 0. But within 1 millisecond, 0.1 millisecond, the current still flow. So the time, the picture here, we are talking about in millisecond or maybe a fraction of millisecond, right? Fractional millisecond. So the current still like that. So you remember what kind of the time domain we are talking about. If time domain talking about in minute, of course, you can see turn off, the current go down. But here we're using high frequency switching control, then we can see the IA there. So now we understand briefly about operations, but more importantly will be, since we ignore something, we are using pulse width modulation applied to the motor, and then we are using square wave applied to them. Then the inductance, we are not purely using a DC. We are now using a switching waveform. So if apply a square wave to an inductor, can you guess what will happen to the current? Square wave? You can see that if apply a square wave to an inductor, once we turn on, then according to L di dt unit voltage, then inductor current will therefore go up, must be. Yeah. So this di dt go up. And then if we now apply 0 volt, because diode we're going to turn on, if we turn off the source, then that will 0 volt, then the current may therefore equal to 0. But of course, later on you see that it's not equal to 0. If then 0, if di dt is 0, then it will flat. But actually it's not the case. Di dt will become negative later on. I've showed the equation. If the di dt become negative, 0 something, then you become like this, if negative. So that means the inductor current, if positive voltage on the inductor rising, if a negative voltage will be dropping. If low voltage will be horizontally flat. So that's what we're going to see if we going to change the voltage to the inductor. But now it's not only inductor. For motor, we got RA, resistance, inductor, and the back EMF. Let's see what happens. So that's the model. Then the equation is still unchanged. That's a motor equation. Those are the most important equations you all need to memorize. Then now they can see that I changed everything into lowercase. Why is that? Because we know that the voltage is no longer a fixed DC. It's now become AC component, changing with the time. All the component parameters here are changing with time. So the input voltage, we know that it's square wave, right? The EA voltage could change with the speed. If the speed change, the flux change, then that can be also changed. We don't know yet. We use a lowercase represent. It may be changing with parameter. The current, because we know that once we have inductor, the current may be rise, drop, and so on. So IA no longer a pure DC, could be a ripple current. So that's why I use lowercase here. And then, so that's why this current is also lowercase. LA and RA is a fixed circuit parameter. RA will be fixed depending on the copper you use. Inductor depends on how many turns you use, right? So that means LA, RA is constant. I can use uppercase here. So my terminology will be usually for everybody in power or electrical. Uppercase usually means fixed parameter or DC parameter. Lowercase means AC parameter or variable or changing parameter. That's the terminology we use here. So that's it. So even though in the future, when you write up your paper, do remember how to distinguish between uppercase and lowercase. Don't everything use uppercase. Only the uppercase for fixed constant DC parameter and lowercase for variable changing parameter. Okay. So that's why the equation is still the same. This equation This equation is just based on Kirchhoff's law, never can be changed. But the component parameter inside I need to modify a little bit to make sure you understand the difference between AC and DC component. Do you get that? Have you learned that in the past? For all the electrical or engineering parameter, we use AC and uppercase and lowercase?
No.
Okay, now you know. So in the future, when you write up any paper, remember uppercase and lowercase, what are the difference? Anyway, so the IDT is the voltage drop across the inductor. So that means this component will voltage across here. And this component obviously the voltage across here. So that's how we get the equation, right? Of course, IARA is the voltage across the resistor anyway. But we know that later on, or now we know, because we are applying a square wave to the motor, then there must be some ripple current in the inductor. How large it is depends on the parameter, depends on the switching frequency, depends on the inductance, depends on applied voltage. But we know there must be something. But to assess the voltage across inductor, we firstly build to check that equation again. Because that's the equation. But the input voltage here will be from the switching DC circuitry. So we can rewrite the equation, putting the IDT on the left-hand side. Then we can therefore look into the component. So when transistor being turned on, the voltage V in here are equal to VDC. Yeah. But when we turn off, the dial become turned on. If you're putting a dial, will be off and on, right? Then that will become 0. So that means this parameter we can therefore rewrite in here become this configuration. Okay, so now then you can see that the voltage impressed on LA is no longer a pure DC, but with a variable voltage. Sometimes this will be positive, because input voltage must be greater than the back EMF and also greater than the voltage drop on the resistor. And then when the transistor being turned off, the DC input voltage becomes 0, and the back EMF may dominate. The back EMF cannot change instantly. The back EMF are controlled by internal winding, the flux, and also rotational speed. The motor cannot change the speed instantly. They still continue voltage within milliseconds. So that's why the voltage is still negative. So this negative voltage all there will force the inductor current will drop, not linear, but drop. So you can see that increase and decrease. So that's positive, that negative. Negative will be in here. Positive will be in here. All right?
Can
Get that?
please,
Okay. So
when
when we turn on the transistor, the voltage across this term will be positive. Positive. Because that's a conventional concept. Input voltage, VDC, minus the back EMF, minus voltage drop, still positive. Fair enough. That's what we have been using. But when we turn off, then the input voltage in here, you see, input voltage on here becomes 0. 0. Then the voltage across here we have this three component control them, but this equal to 0. So if you look into the inductive voltage here, then the same equation, just like this V in becomes 0. So remaining term will be negative. So that is to say the effective voltage applied across the inductor is negative, just purely from the equation, without any ambiguation, right? Before it's not negative because we got a high voltage input, but now this voltage disappeared, so it become negative. So that's why inductor current is dropping. So that's why I can see that this is the IL. So the current will therefore go up and down in this manner. Certainly the ripple for all the motor design tend to be really small, just a few percent. It won't be large percentage. It won't be 50%, 60%, 40% is too large. Just a few percent, maximum 10% for all the motor design. So this small percentage, you can see the current is still IA, constant current, but you can still some moving there. Later on, we'll discuss why we don't like that kind of ripple. But bear in mind, you can see that if you look at more detail, you can see this kind is the waveform we are going to see. Okay, you get that? I think you learned that, right? When the DC motor, have you learned using switching waveform or just pure DC when you're in the undergraduate?
Didn't touch that much.
Okay. How about Shito? How much did you learn for DC motor?
I have not learned the DCMotor, but I have learned some like the converter including the current change in the inductor.
Okay, so this part you have learned them in the
Yeah,
past.
it's a kind of video.
Okay, Serifo, have you learned that?
Just the basics.
Basic. How about this switching voltage to a DC motor? Have you learned them? No. Okay, now it's something new. How about Manvia? No, it's good. So it's a quick revision, then you know. It's really basic and important. You all need to know. So next thing, we do the waveform more in detail. So now then we change the IA current become a ripple current with average value same as before, like this one, but now become ripple, right? Going up and down. But basically still have a main DC component for the main current. But because IL are up and down, we see this ripple. So that is to say the inductor, the armature current. So IA, we have two components. One is the ripple component, AC component. Another is DC component. So average is uppercase IA represent the DC component plus some harmonic here. Look like this ripple. So this current will flow in two mesh loop. So when the transistor being conducting, this current will flow through the transistor. So when we turn it on, go through here, okay? And that's why you can see that the IDC here will therefore like this. So this one, they are equal to each other because the current are conducted by the transistor. So the input current, which also equal to transistor current, they supposed to equal to each other. Okay.
So, I understood that the armature current that can increase suddenly.
Yeah.
But the DC source current, why the
Yeah. You can see that it's too small print. That's a DC current. This current, right? This current will therefore, when this conduct, this current will just flow in this way. So this current is armature current, IA, right? So this current therefore equals the IA will flow in here. But the name I put here is IDC, DC side current. So that's why IDC current equal to IA. So these two are equal. Because conducting, the transistor conducting these two current. All right, Serifo, do you get that? Okay. Manvia, do you get that? So that's why this kind of the shape will appear in here. These two are exactly the same. And the next, so that's an on. When we turn off, then this current will therefore flow in this loop. So the IA current, this one, will therefore need to conduct to the diode. Okay, so the diode current here will therefore conducting the second part of the current. So this trapezoidal shape will appear in here. So these two are equal. These two are equal, okay? I just show you which current is which. Very straightforward. All the power electronic current are using this method to present. So you need to get used to it anyway. And then, of course, when we turn on, the motor voltage, of course, equal to the input voltage because the transistor is conducting. And then next, the motor voltage equal to 0 because the dial is on. Dial on, so motor voltage must equal to 0. So that's how we get the waveform. All right? Straightforward, do you get that? Very simple. This waveform is really straightforward. Don't have any confusion. Just directly copy from depending on which transistor or dial is on. If you learn the chopper, maybe if you learn the buck converter, it's exactly the same. So that's now then I go to the equation. The equation is still the same. Still the same. But because now then the voltage, although I use lowercase, but now I know the voltage here is equal to DC voltage, so I can put the VDC in here. The back EMF, although I use lowercase, but I know if the motor under stable condition, like the rotation speed is unchanged, I can use uppercase because it's constant back EMF anyway. We're not talking about we changing the motor voltage, we're not talking about we changing the motor speed all the time. We just constant motor speed are rotating a certain speed. And so we now have this equation. So that is to say IA is now increasing. IA is now increasing. And the transistor current equal to the input DC current. We discussed that. And the next will be for second region here, which is in this region here. Then we just discussed the VDC, the V input here, equal to 0. Or regionally, we have the input voltage, but now becomes 0. Then we only have all the negative term. Negative. Then we can see that the current is now decreasing. L di dt. So the diode current, like this one, this statement equal to this, right? The diode current equal to the armature current. Very straightforward. Okay, I just repeat what we said just now. And then you need to familiar with the waveform. This is the typical waveform we use anyway. So if anyone hasn't done any chopper, simple chopper or buck converter, maybe slightly new to you, but they are not complicated. They are really straightforward. All right. Any question up to this point? Any confusion? Okay. You're a postgraduate student, you should know. So next, more importantly, we like to understand more about the ripple current. How much ripple on the armature? Why is that? Because the ripple current, all the current are proportional to the torque. So when we control a motor, we don't like the motor have too much torque. You see a motor torque will control the rotation. If there's a motor torque, do you know what happened to the motor, to the shaft? Some kind of vibration, shaking. Look like the shaft are shaking because of the ripple. So we don't like that. If you use the motor for electric vehicle or for a robot, I don't like the robot shaking the hand. Impossible. So I need to control the ripple to be small. How small? So small it won't affect the operation. For example, like if the robot shaking the arm, if the shaking less than 5% of its movement, probably you can't see anything. If less than 1%, of course, you won't feel anything, right? So that's the thing we tend to be as small as possible. So now then, this is the basic equation when the current going up, right? So this amount, we call it the delta IA, is of course the rising. So we just using this equation, we can therefore work out how much the current moving up, going up, rising up. And the duration here, the dt here, is just equal to the duty ratio. T is the period. Yeah, the dt, the whole dt mean this duration, right? dt. Then that will be equal to dts. Okay. Ts is the whole going up and down, right? So this is the period ts. This is the dts. So this is 1 minus dts. Okay. simple ratio. I think we discussed that before in the a few page here. Yeah, that's DTS, and this will be 1 minus DTS. So this width. Okay, so that means this will give you rising. The same equation here will give you the falling part here. Then the duration here, we use 1 minus DTS for the dropping ripple. So the equation here based on the original dIdt equation, right? So these two rising and falling, they must be equal to each other when a motor becomes stable. Because this ripple, we see that this will go like that. So that means this amount go up, amount go down. The amount go up, go down must be equal all the time. Otherwise, the motor will behave like this. Okay. If go up more than going down, all the current will be moving up. That's not a right thing to do, right? So that means these two must be equal to each other. The amplitude must be equal to each other during the stable condition. So that to say these are equal, I mean the amplitude equal. One go up, one go down, the summation equal to 0. You won't have any lag increment. So that means these two summation equal to 0, then we can resolve the equation. Many items can be cancelled out, then go down to this equation, which happen to be this term. You see, when you compare to the equation we have for last week, this term equal to input voltage to the motor, but now the voltage become duty ratio multiplied the input voltage because we have to got the duty ratio to control about the average. So the equation is the same as before, no change. We're just changing the input voltage, controllable by the duty ratio. That's all. And then for the back, so next, then we can the frequency we can also using the same equation to work out. That will be just replacing the input voltage instead of the source voltage become the D VDC represent the source voltage and minus the voltage drop on the resistor. That's all. So the two equations exactly the same as before, but we're changing the voltage from a constant voltage become a voltage controlled by the duty ratio. So now then we got these two working equations now. So, but we like to simplify the analysis, especially during the steady state. So during the steady state, anybody can tell me what's the meaning of steady state? This term has been used for all the technical paper. When we discuss any motor, power electronics, we usually call steady state analysis. Right? What's that mean? Steady state?
Not changing.
Not changing, yeah.
Continuous current.
The current may not be continuous. That means the system can go to a stage. That means may not have any big change.
Okay.
And don't have any change in the power.
Maybe
I should say.
Period. The system display the period. Like whatever CCM or DCM, that is a steady state.
For instance, when you charge an inductor, after you turn on the switch, charge inductor for a long time, after a few seconds, the inductor current becomes stable. That's called steady state. Yeah, steady state. When you drive a vehicle in a motorway, right? When you press the pedal, you control it so that the motor at 70 miles per hour constantly. That's steady state. But once you overtake other vehicles, brake, it's not steady state, it's transient state. So now that I say, oh, the motor now we are assuming it's still in steady state. We're still using a square wave to control it, but we know the waveform go up and down. But this up and down, the current is always keeping the same up and same down. We still call it steady state. So that means in here, the one thing we said just now will be the back EMF. before we use lowercase, we think the speed could be changed. But now I assume under the steady state, the motor under the constant speed. So this term will be unchanged. So we have this term now. We use uppercase to represent it. The current, just now I use lowercase, but if we only calculate the rising, to make easier, I can just using the average current for that triangle, for that trapezoidal, to be this IA. That's good enough. The ripple usually small, only 5% or less. So the IA current, although there's a less, this is higher, but I usually use IA current to estimate the voltage drop on the resistor. That will be good enough. So I can use uppercase IA to do that. So the whole thing, I can use this simple formulation, ignoring some of the variation. If you use a triangular way here, it will be really complicated. I see that when you use a DC average here, that is sufficiently good. So that's how we calculate ripple. And also, I mentioned about the back EMF. When the speed is unchanged, constant speed motor, then we can assume this is a constant anyway. So the input current appears in a DC source. The DC input current is square wave. But because it's simple square wave, I can just get the average current equal to D times motor current. That is also the average current. Instant current equal to IA, but average current, we can still say equal to duty ratio times IA. All right, so that's to say that is the input current in the DC source. We're going to see that square wave like that. But the whole waveform, if we use average meter to measure, the green line here will give you the average value. Just like the whole waveform, we're using integration to average it. That will be the green line. So that basically will be equal to the duty ratio multiplied by IA. No ambiguous, just really simple as such. I think you all get that. If you learn the electronic buck converter in the past, 100% simple and easy. But the first time you learn it, you need to think about for a few seconds, then you know it. Okay. Any question? Servo, do you get that? Okay. I'm just checking. You don't have so much background in Power E, but they have. So if you understand, they all should know.
So just one question. So here, if we are taking the average, why this average is little lower?
Oh, because duty ratio. You see,
Okay.
your red color is the waveform. Here we got 0. So something plus average is 0, we got lower. So that's all the thing, the whole waveform average. If only average on that triangle is this one. If average on the whole waveform becomes this one. The motor will see that everything. On the input side, the input battery, if they connect the battery, the battery only see this green color. Although battery is still able to see the trapezoidal waveform, but the average current for the battery will be still lower DC. So let's see a typical example, then with some calculation, then you see how much understand it. It's very straightforward anyway. If you did the DC motor in the past, in the undergraduate, that was some common question you can see there. So we have a DC motor, separate excited DC motor, and powered by DC converter. So this is really simple DC converter, actually a simple chopper, right? But we can still call DC to DC converter. The input side voltage from the DC source, the VDC equals 600 volt. So here will be 600. And the parameter will be shown in here. So 0.05, and then we have 0.05. We got K equal to this one. IA, this all we have 250. We assume the current being controlled at 250 amp. And the duty ratio here, the transistor, you are using 60% duty ratio, and the frequency is 5K, and the inductance 0.6. So do remember, I mentioned to you quite a few times, the inductance, the Henry is the unit, but Henry is really, really large unit. So we use it for all the inductor in the transformer or inductor or in the motor, you use it in the milliHenry. But in high frequency power electronic, we use microHenry. Okay. So so that means don't try to design a motor with a few Henry. Impossible. That's just like a big animal. Impossible, right? So if you see some textbook, they use Henry, that means they don't understand power. So now we ask you a few questions here, including input power, the equivalent input impedance, the motor speed, motor torque, EMF, and the ripple torque. Okay, let's see what they say. So now you go to power, I'd like to look into that. So in the average armature voltage, this voltage across the motor here, V lowercase v in is a square wave. So as I said, we can use average voltage, duty ratio times the input peak voltage to get that. So that's why we can say duty ratio times the input DC source voltage, 0.6 times 600. That is the input sine voltage, average voltage the motor will experience. Although the motor experiences 600 volt peak voltage, but average voltage, the motor experience only 360. Because this voltage will therefore appear on the magnetizing, so that's how the motor will feel. The motor is quite slow response. It's such high inertia. So that means you use transfer voltage, you just feel all the average voltage. And the input power from the DC source, our basic equation will be IDC VDC dt. That's a basic power equation, right? We know that. And then, of course, in here, we need to average. That's the energy. Then you average them with the period, right? Average with the period to get the power. And then in here, the DC voltage is unchanged. You see this is VDC voltage. The DC voltage here is not changed anyway, fixed DC. We don't have any switching square wave here. That side is square wave, but this side is a pure DC voltage. So for this equation here, then the VDC is constant, we can just average. Okay. So this is average by definition, right? Integrate the current. Average, that means that is the average. So by first principle, then we know that this, to get the power from the DC source, pure battery source or DC power supply, we use average current. Purely we don't use RMS because this equation. Okay, you get that? So don't use RMS meter to measure the current for DC source. If you're doing DC to DC power converter, then you have a DC converter input and output. You measure power in the input, don't use RMS current meter, use average meter. Many meters, they will say true RMS, that's incorrect. You get the wrong answer. The difference by 50%. Anyway, so you get that. So this is many students or even many PhD students, they don't understand that. When to use average, when to use RMS. Because this equation. So again, the power from here, and of course we need to integrate by TS. So now the power for the motor. You see this is current. This current for the motor is fixed, right? Although there's a ripple, ignore the ripple for the moment is fixed. So that is, in here we can see that PM equal to 1 over TS IA V in dt. So IA is a constant, we can put it in the front, and then 1 over TS. So this term is the average voltage, right? Average voltage. So that's why we have 250 amp multiplied by the 600 volt. That's the average voltage. Average voltage for motor. So that should be lowercase. Oh, that should be IA. Yeah, that should be lowercase. this voltage. Still a square wave, so we need to get that should be average voltage. It's better to change the symbol like that. That will look more reasonable. Okay, you get that? So this is very common equation. Everybody know, but sometimes even that they know, they still confused about RMS current and average current. That's the most basic formulation we shall use. Okay, do you get that? That I think you may say, how come, Professor, you teach us so simple power? Everybody knows when they in year one, but I have quick revision to you all. Make sure you understand. Because before this lecture, when I ask you, use RMS meter to measure current, is it correct? Maybe you say yes. But now you know for DC, you need to use average current meter, not RMS. You get that? Okay. So now your duty will be go back to ask your friend to see how much they understand basic current or voltage measurement, when to use RMS meter, when to use average meter. I guess many of them may not understand. Okay. So when we go to the AC motor, then we discuss about RMS current measurement. Anyway, so now then that's quite clear. Now we have the voltage and current, the input current with the average them. 250 amp is the motor current, IA current. Input side, we are chopping the current by the transistor. So that's why we have 60% in here, become 150 amp. So input current in here become 150 amp. So now then you can see that for the input side, the DC source, we have 600 here. We connect with a transistor. This will join about 150 amp. So here we have, this will be 150 amp. This was 600 volt. So we can use this voltage and current to estimate about the impedance. So the converter itself in here, if I have I'm a power source here, I will have a look into this circuitry. The DC source here will only see an impedance, a resistant impedance. That will be controlled by how much current we draw. So the impedance you can see here is just this voltage divided by this current. That's it. So that means when we do that, then we can, by the simple first principle, the input impedance we can appear by the DC source will be equal to VDC over IDC, 600 divided by 150 become 4 ohm. So that means the whole thing here, considered by the DC source, only look like 4 ohm. Okay, fair enough. It's not equal to 250 amp current, but more look like 150 amp current become 4 ohm. Then we can use the previous equation from the speed to calculate about the speed of the motor, right? So now this is the average voltage. We put all the parameter here, then we get 91 radian per second. We found that many engineers, they don't like to use radians per second because they don't understand radian. So we change them into RPM, 60 over by 2 pi RPM. We tend to use RPM. They more understand about RPM anyway. So for the torque, again, torque constant is given 3.8 multiplied by the current. You see the current for the motor always the same. We are not chopping the armature current. The armature current is always there. Okay, become 954. Back EMF is based on the constant speed here, 91. So we have 347 volt. Okay, so A to E will be simple. So now then you come to a stage where not why the voltage for the back EMF is 347, so low. Our input voltage 600. Because in the past, in the previous discussion or the slide, the back EMF usually slightly lower than the DC voltage, right? Slightly low, only lowered by 10% or at most 20%. But now here, 600 is dropped to about 344, drop nearly half. So instead, all the voltage go to the transistor, or go to the winding resistance? Would there be a problem to burn the motor or burn the transistor? That's a high voltage drop. What do you think? Would that be a big issue?
This is due to this duty ratio, right?
Something like that. That's the question I tend to ask you. But my comment here is the back EMF here 347. The input voltage here 600. Would that mean we've got large voltage drop in the system? Would that large voltage drop will cause an inconvenience or damage to the system? What do you think, Stefan?
Current difference.
Sorry, say again? What?
The input current and output current difference. There's not a very large energy loss, so they will make a lot of heat. So I don't think that's a issue.
Okay, Matthew, what do you think?
I think that it could be an issue.
Okay. Sherful, do you think we have a big issue at such a big voltage difference?
It will increase.
I don't think so, because due to that duty ratio, the current which we see 250 is now 150. So it's not going to affect that much because the current is low.
In here, I'm mainly concerned about big voltage difference between the input DC voltage and the motor back EMF. The difference by nearly half. But that is not a problem. Why is that if in the average voltage across the motor is not 600. It's 600 multiplied by the duty ratio. It's 360. So the average voltage motor C across here is 360. 360 compared to this one, only about 13 watts different. It won't have any damage effect to the motor. That is the same as all the tutorial we did in the past. The voltage input compared to back here only different by just a few percent. In here, although input from the left-hand side is 600, but that is before the transistor switching. So the motor itself is a really stupid animal. You only feel about 360 volts. So that's good enough. It won't cost anything. All right? That's what you mean. So that's why we need to use switching transistor to ensure that the average voltage go to here, not 600. We try to switch them into much lower voltage, closer to the back EMF to decrease the voltage drop in here. Only a few percent of voltage drop, that is reasonable. Okay. That is the theme of the story here. We use chopper, simple chopper, power electronic chopper to adjust the voltage to the motor. That's the key. True. So further discussion will be how about the torque? You see we got the torque ripple as I mentioned. So the delta IA is the current appear in the motor current. So this is strictly 600, the back EMF and the current times the RA. Also the DTS equal to 60% of the frequency, C period. Then you give you 14.4 amp, right? So again, we use 5 kilohertz, so the period will be 0.2 milliseconds. I put all the parameters in here. So 14.4 amp is the peak-to-peak current ripple. So this ripple will also appear in the peak-to-peak torque ripple. So the torque ripple is 55 nanometer. So 55 nanometer is quite a large nanometer, right? Quite a large torque. But however, compared to the main torque is 954. So only about 5.7%, reasonable good. So the ripple I usually try to make it around less than 5%. Around 5% is good. 10%, 20% too large. You can see the vibration. 5% you won't feel anything unless you have to go for really precision motor. If some motor you need to do fabrication for several nanometer, then that will be another story. But most of industrial drawing, 5% is no problem. So that's to say we prefer for no ripple, but that's how to make sure then we have no ripple. If you want to, second question would be, if you want to further reduce the ripple torque, what can you do for this tutorial?
frequency,
Frequency.
increase the frequency,
Yes, which frequency?
the transistors.
Yeah, increase the transistor switching frequency. Then Fs increase, Ts this
Decrease.
increase this one this one will therefore decrease. Then this will be decrease. This will be decrease. The whole ripple will be lower. So then you can see that if I'm using 5 kilohertz compared to 50 kilohertz, I can reduce the ripple down to 10%. That's what we need to do. The high frequency is better, but high frequency that means you need more expenses for the transistors, the control circuitry. So that's the pros and cons. That's all for today. Next time we'll discuss something further about the conclusion. We're going to finish now. So I will going to post the homework maybe tonight or maybe tomorrow. We've got 10 days to finish it. Yeah, okay. Any question? Okay, then see you next week then. Okay, bye for you.